Hello everybody, I'm Michael DeBose, and this is my fourth lab, which will be covering oscillating springs. So the goals of this lab is to explore the motion of an object subject to a spring force. How are we going to do this? We'll use Tracker to analyze this type of motion in a video provided by the course instructors. We'll compare this to a computer model of the same scenario that we're going to code in GlowScript. So first you have to understand, as always, Newton's first and second laws. Here you have your basic kinematic equations, um, as well as a couple new concepts we've learned recently. Hooke's law, being that the force of a spring is equal to negative kx, as well as the work energy principle and all of the various formulas that can be derived from that. So here's the tracker info. As you can see, the graph follows a sinusoidal type of equation, and then that seems to be the pattern that it's following here. You can see that we have the position initial, the initial velocity, the mass, and so on. Also, we finally have used all these pieces to calculate a relaxed length of 0.036 meters. So here's our code. This is our model that we're going to set up that we're trying our hardest to make look like the original tracker data. As you can see, we clearly have edited these lines. As you can see here, you have the force of gravity is equal to the vector of 0 in the x direction, 0 in the z direction, but a negative force of mass times gravity on the ball. This calculates the gravitational force, then the spring force, as you can see, which is clearly negative ks times L hat. All right, so next, our model here, observed versus predicted. Our observed is red and the model's blue. The difference in between the models is most likely due to an uncalculated forces and possibly miscalculations of the K value. There are quite a few forces that could be acting on it, and I believe this to be the reason that the model is very consistent in its oscillation, while the experimental data seems to be acting with a smaller and smaller period with each oscillation. Next, we have conclusions. So, is the energy principle preserved? Yes, the energy principle is preserved. As you can see here on this graph, the orange represents the net energy, the change in energy in joules. The blue shows you the kinetic energy, the red shows you the spring potential, and the green shows you the gravity potential. The gravity potential and the spring potential even each other out, and the kinetic energy is centered at 0 and oscillates back and forth across the x-axis. As you can see here, there are temporary changes in the kinetic and the potential energy, but the total energy stays constant as everything else is oscillating. So what does it mean? We had to make an estimation of the period based on the x and the y oscillation. So on the left you can see the x, and on the right you can see the y. So we calculated 8.167 divided by 5, which is equal to 1.633, and calculated based on y, we ended up with 9.117 divided by 6. Thank you very much. I hope you all have a wonderful day.